Lesson number 2 of Chapter 3, Part 1. This is the second lesson in the Introduction to Forces packet. The lesson is called Net Forces. Now, what I'd like you to do first is to spend a few moments doing the warm-up problems, just problems 1 and 2, and then start the video up again and check your answers. Warm-up number 1. What is meant by a company's net income? That is the total income minus the expenses. How does this relate to the lesson? Well, we can imagine that since we have the title of net forces, that somehow we're going to be subtracting forces or combining forces together. That'd be a good guess, and we'll see if we are right. Question number 2. What did we do last lesson? We classified forces with 3 different kinds of systems. We had one system that related the forces to how they changed the shape of an object. In that system, all the forces are either classified as tension, torsion, compression, shear, or bending. Or in another system, we can classify all forces as being one of the fundamental forces of nature, either electromagnetic, gravity, strong, or the weak force. In a different system, a third system, we can classify all forces of the entire universe as being either a field force or a contact force. So if I mention any kind of single force, you could classify it in 3 different ways with 3 different words. We could have a contact force that is electromagnetic and compression, for instance. Okay, next. Number 3, see a death-defying demo of superhuman nail-resisting ability. I'm sorry you cannot see that on the video. You're going to have to see that in real life. Would you please spend a few moments now looking at the purpose, relevance, and success statements, and then go ahead and read the 4 paragraphs of the introduction. Please pause the video to give yourself time to read all of that. Next, we're going to look at one-dimensional problems. These are all really easy, I hope. Find the net force on each box by adding the vectors. Redraw the vectors head to tail. You end up either adding or subtracting the numbers. So for question number 1, we have here a picture of a big person pushing with a force of 10 pounds and a little person pushing with a force of 3 pounds. Let's pretend that this is me and my daughter pushing on the refrigerator to move it across the kitchen floor. So what we're going to do is, notice we've had the 2 forces drawn to scale. The 3-pound force is a smaller arrow than the 10-pound force. That's the way we do vectors. Draw them in proportion to their numbers. Okay, I'm going to draw them head to tail, so it's going to look like this. The tail end of the smaller vector is going to go to the tippy top head end of the big vector, and so I draw them like this, where one arrow ends in the pointy tip, the other arrow begins with the blunt tail. I believe that some teachers don't call this going from head to tail, but rather tip to tail. Either way works. So once you line up the 2 vectors head to tail, we then draw the final answer vector from the tail of the first to the head of the second. And you can see here the length of that is going to be 13 then, and so that's our answer. That's the net force on the refrigerator, 13 pounds. And to be more specific, we need to say it's 13 to the right, or we could have 13 with an arrow pointing to the right, but we have to have both the magnitude and the direction somehow shown. Question number 2. We have the 3-pound force pushing to the right and the 10-pound force pushing to the left. So when we redraw this head to tail, I draw the big force And then where the big force ends, the tip or the head of that, I start the tail of the other force, and that one is going to the right, so I backtrack. The answer is going to be from the tail of the first to the head of the second. And the distance here, you can see, is going to be 7. We end up subtracting when these forces are in direct opposite direction. And so we have an answer of 7 pounds of force to the left. What this means is, even though there's 2 people pushing on this refrigerator, the refrigerator is going to act as if there's only a single force of 7 pounds pushing to the left. In our previous example, the refrigerator is going to act in the exact same way as if just one person was pushing on it with a 13-pound force to the right. Okay, now let's look at the last situation. We have 2 equal forces of 10 pounds pushing in opposite directions. So I draw them again, head to tail. The first force going to the right, and where the head ends or the tip ends, I start the tail of the second, and it goes in the opposite direction, and we end up in the exact same spot as before. There is no net force. These cancel out. They are equal and opposite. So the refrigerator is going to act as if nobody is pushing on it at all, which kind of makes sense. If you think about 2 people pushing equally on opposite sides, the refrigerator is going to just sit there. Next line. The picture above shows force diagrams, in other words, free body diagrams. Let me move the camera up a little bit so you can see the whole phrase. Okay, these free body diagrams show the direction and the magnitude of all forces acting on an object. Actually, the force diagrams above are not actually complete. They are missing a couple forces. They're missing the forces of gravity pulling down on the refrigerator and the forces of the floor pushing back up. We're not going to complete those with those extra forces. We're going to go on to the next page. On the back side, drawing force diagrams. We're going to draw force diagrams for each one of these situations. We're going to indicate the net force, if there is one. Now I'm going to be drawing shapes that are appropriate for the objects being involved, but you don't have to do that. For a force diagram, you could just draw a circle for each object, or a square, or a lot of people just simply use a dot. Those things will represent the object, and then we will draw arrows to represent the forces. The arrows are going to be in the appropriate direction according to the push or pull of the force, and the arrows are going to be different lengths. Longer arrows are going to represent bigger forces. So, question number 5. Let's zoom in on this a little bit. Let me move the camera. We have a rocket launching. We want to show the force of gravity and the force of the exhaust. So it's going to look like this. Force of gravity going down, and we're going to label it with a capital F and subscripts. You could just simply have a subscript of G if you want. I chose to put GRAV for gravity just to be a little bit more explicit. And then we have the force of the exhaust. That's the force of all the flames and smoke and all that from the rocket engine. Now, this rocket is in the process of launching, so that must mean that the force of the exhaust is pushing up really hard, harder than the force of gravity pulling down. We have a net force going up, so we have an acceleration upwards. If the force of the exhaust was not greater than the force of gravity, then it would not leave the ground. So make sure that your arrows have one longer than the other, the longer one going up. It doesn't really matter how much longer you have it. We don't know the exact numbers here. Number 6, a car coasting to a stop. And I tell you that there are 3 forces acting on this car. the diagram is going to look like this. The force of gravity and the force of the ground are the same length but acting in the opposite direction. We know that they're the same length because the car is not accelerating upwards or downwards. It's not sinking down to the center of the earth. It's not flying up into the air. So the up and down forces are equal and opposite. We're given just one other force, the force of air friction, so I have that pointing to the left. You see another reason for me abbreviating gravity here as the 4 letters. If I just had F with a little g here, it might be confused with the force of the ground. Another way of alleviating this confusion is I could have called this the force of the road with a capital F and a little subscript R for road. Perhaps someday I'll change the lesson to include that word instead. Number 7. A heavy ball is dropped into water. Would you please cross off the second sentence? I don't think that is appropriate. And here is the picture that goes along with it. Just have a round circle for the ball. Force of gravity pulling downwards. F with a subscript G for force of gravity. And the ball is still going to be falling downwards, accelerating down and down. It's just simply not going to be accelerating as fast as before. And so we have the force of the water pushing up. Force of the water upwards is not as long as the force of gravity. So therefore force of gravity is bigger. It's still going to accelerate downwards, just not as much acceleration as before. Number 8, a race car speeds up. So there are going to be 4 forces acting on this. We have the force of the road and force of gravity, just like before. Equal-sized arrows, but opposite directions. We have the force of the motor, which is pushing really hard forward, and then the force of air friction, once again, pushing backwards. Since this car is speeding up going forward, that must mean that the force of the motor is much bigger than the force of the air friction. So we have a net force going ahead, giving it an acceleration. Number 9. A ball is being pushed upwards by a hand that is tossing it. So we have to show 2 forces, the force of the hand and the force of gravity. Both of them are acting on the ball at the very same time. The ball has not left the hand at all. Okay, since it is being tossed upwards, that must mean that the force of the hand is bigger than the force of gravity. And so we draw it with an arrow longer going up. F with a subscript H for hand, F with a subscript G for gravity. Number 10, going down. A ball has just been tossed upward. It has left the hand, and it's moving up into the air. There's only one force acting on it at this time. The hand is no longer touching the ball, so it is not exerting a force on it. The force of gravity hasn't stopped, though, and so we still draw that. And I'm going to draw the arrow the same length as I did before, because the force of gravity has not changed. That's the only force acting on the ball. Number 11. The ball has been tossed and is now moving downward. So it's gone up and now it's coming down. We still only have one force acting on it. Force of gravity going down. And so it's accelerating downwards in the negative direction. In case you're confused about number 10, where we only have the force of gravity going down, but the ball is being tossed upwards, remember that the downward force of gravity means that we have a negative acceleration. It's going to be slowing the ball down. This negative acceleration will be slowing the ball down as it travels with a positive velocity up into the air. That negative acceleration will gradually reduce that positive velocity down to a 0. It'll stop at the tippy top of the trajectory, and then it'll start falling downwards. Okay, so that was number 10 that I just reviewed. We did number 11 already. Now let's go on to number 12. We have a ball. Oh, it's out of focus. Let's try to get it back into focus. There, it clicks back into place. Number 12, a ball has landed and is sitting still. So let's say it's sitting on the ground. So we draw it like this. It is not accelerating upwards or downwards, so these forces are canceling each other out. There is no net force. The force of gravity pulling down is equal and opposite the force of the ground going up. And that's the end. Would you please read what's happening in the next lesson? If you are still unsure about this stuff, you can look at the 2 YouTube videos that are made by other teachers that are listed at the bottom of the page. Or there's the reading that's on the following pages. Please go on to the homework.